Hi everyone, this is Nick Fryer, and today we're talking about Physics 2 Lab 3, which has to do with circuits. So just as a quick introduction, our experiment consisted of a bunch of different types of circuits with resistors and or capacitors that were either in series or in parallel. And the idea is to predict the behavior of the circuits and compare that to the real life results that we measured using ammeters for current and voltmeters to measure potential differences. Quick conclusion, the current in the two resistor series was about 0.0155 amperes. And in general, this value and others did somewhat match what we expected, but there was error in pretty much every step. And just in general, a greater resistance in a circuit results in a longer time for capacitors to charge and discharge within that circuit. So just as some fundamental principles, first we have the node rule, which says that the current entering a node, which is the split point that turns into two wires, equals the current exiting that node. And this is from the conservation of charge. So current in equals current out when you add them up. And the loop rule, which is derived from conservation of energy, which says that as you loop around an entire circuit back to the beginning point, the difference in potential is zero. There's also the idea of resistance, which is determined by Ohm's law, where resistance is voltage over current. When resistors are in parallel, you kind of get this weird equivalent resistance formula that you can add up. And in series, it's a little bit easier. You just straight up add them up. And then there's the idea of capacitance, which is how much charge a capacitor can hold per unit of potential difference. So it's charge over the delta of the potential difference, or just epsilon zero times the area of the capacitor plate divided by the distance between the two plates. Next, we have a couple quick circuit diagrams that kind of represent what we did in the experiment. One is just the series circuit with two ammeters and two different resistors between them. And then we have the RC circuit, which has one resistor and one capacitor. The system was the ammeter and voltmeter that we used, and the surroundings was the circuit and everything else outside of it. So first, we constructed a simple series circuit like the one you saw in the previous slide. The series circuit had two 1.5 volt batteries, so a total of 3 volts, two ammeters, and two resistors, one 47 ohms and one 100 ohms, connected by metal wires. The predicted current was about 0.0204 amperes, which you can see the calculations below, and the measured current was 0.0155 amperes, or 15.5 milliamperes, which just became negative when we switched the leads of the ammeters. So relatively accurate, but there was some error. Part 2, we did the same thing, except we switched out one ammeter with a voltmeter, and we predicted a potential difference of 3 volts, but a current of 0 amperes, or approximately 0 amperes, because the voltmeter has such a high resistance that really no current is flowing. And this is about what we saw when we measured out. Part 3 was around a circuit. We measure potential differences at the different red dots that you see in the top right there. Across the battery, it was 2.3 volts. And then across each resistor total, we got about negative 2.2 volts and 0 volts everywhere else. So this supports the loop rule. Even though it's 2.3 volts instead of what we expected, the 3 volts, the difference, the sum of all potential differences was about 0 volts, which is what we expected. Next, we put an ammeter parallel with the resistor, the 100 ohm resistor in this case. The predicted current was 0.06 amperes, just by the same loop rule and node rule calculations, very similar to what we did before. And the measured current was 0.0535 amperes. So there was some error, and this could be accounted for by a couple different things. Next, we have new resistance calculations. So we used Ohm's law again to calculate the resistance of the actual resistance of the different resistors, which was slightly less than we expected for both of them. So instead of 47, we got about 45 ohms, and instead of 100, we got about 96.8 ohms. The ammeter and wire were measured to have approximately 0 resistance, which is what we expected. Next, we constructed the RC circuit with two 1.5 volt batteries, a 1 farad capacitor, and two light bulbs. One that had 10 ohms of resistance, and the other 20. We measured the time to charge the capacitor and discharge the capacitor, and this was longer for both, for the 20 ohm bulb versus the 10 ohm bulb, which makes sense because when you have a greater resistance, it's harder for the charges to move, and so it takes longer for the current to completely stop. So there were some sources of error. Mostly due to human error and just inaccurate voltmeters and ammeters. Wires were old, batteries were old. The ammeters tended to be running out at times and kind of glitching out. So there was a general error there, as well as lack of decimal precision in the measurements that we were given by the voltmeters and ammeters. There's also human error, like stopwatch measurements and decisions on what value to put when the readings fluctuated between different numbers, like 15.5 and 15.6, for example, and just general rounding error during the calculations. And we also assume that ammeters and wires considered had almost negligible resistance, which is not necessarily true, and that the resistors were actually 147 ohms, which we saw before that they weren't exactly that, and this was true when we measured them as well. Just as a quick discussion, if we charge the capacitor with no resistor in the circuit at all, we expect almost instantaneous charging time, since there's really nothing to slow the current down. There's really no resistance. In reality, it was fast, but not as fast. Although there was some error because the current is slowed a little bit by the actual resistance from the wires and the ammeters that they exhibited. Thank you.